Good morning guys. Welcome to another session. This is the fourth part of our complex analysis lecture, and today we'll be mainly covering the residues, how to calculate residues, how to calculate contour integration. Today we'll be talking about them. Let me know if everything is all right, then we can start. So let's start with this residue of a complex function. So anyone has any doubt before we start? Let's take your doubts. Good morning, Harry. Okay, so yes, I remember that Bn terms. Yeah. So here also the same thing has been discussed. Look, residue of a complex function. So we have already discussed this, that let z equals to a be a pole of order m. What does it mean? M number of terms will survive of Bn. So let z equals to a be a pole of order m of a function f of z, and C2 is the circle with radius r which has a center at z is equals to a. So this inner circle C2, outer circle is C1, which does not contain any other singularities except at z is equals to a. So the function contains the only singularity at z is equals to a, and the function is overall analytic in this annular region. Okay. So in terms of r, if you say between small r to capital R, so this is the radius of the small circle and this is the radius of the bigger circle. So in between small circle and bigger circle, this can be expanded within the annulus. The function can be expanded within the annulus, and the Lorentz series has this form: f of z is equals to n equals to 0 to infinity n z minus a whole to the power n, and n equals to 1 to infinity bn z minus a whole to the power minus n. Now regarding the question removable, non-essential and essential, as you can see, if I talk about f of z, so let's say a equals to 0, if we say, so we can have terms like a0 plus a1 z plus a2 z square and so on an z to the power n. So if you only get these terms and there is no b related term, for b related term you see here z is appearing with powers in the numerator, but for b the powers will appear here, right? b1 by z, b2 by z square, b3 by z cube and so on. If there is no b, means if bn is equals to 0, means all these terms are not there. So then that is corresponding to removable singularity. So only terms will appear in the power of z in the numerator, not in the denominator. Now bn, let's say if contain 2-3 terms up to let's say 3 terms, and the remaining term let's say b4 by z to the power 4, we are talking about z equals to 0, na? Here the singularity lies at z is equals to 0. So b to the b5 by z to the power 5 and so on up to infinite terms. So if it happens that these terms only exist, b1, b2, b3 and associated all these things, but the remaining term does not exist. So n has a value from 1 to 3. So in this case we say it is not essential or pole. So highest power is 3, so it's a pole of order 3. If it contains only one term, so this is a simple pole. If it contains up to 2 terms, so this is a pole of order 2. If it contains 3 terms, so pole of order 3. And if it happens that as you have seen in case of e to the power 1 by z, so you see it is 1 plus 1 by z plus 1 by z square, so it will go on up to infinity, right? So Bn has values from n equals to 1 to infinity, so that becomes essential singularity. Understood the basic difference between essential and non-essential? Good morning Murli, Harry, Tamiz. Where is Deep today? Okay, so now look at this. So f of z we wrote as n equals to 0 to infinity n z minus a whole to the power n, and n equals to 1 to infinity bn z minus a whole to the power minus n, where a n is equals to 1 by 2 twice pi I integration taken over c1 fz dz by z minus a whole to the power n plus 1. So previously we write f of omega d omega by omega minus a, so same because we are changing just variable. For bn the integration is taken over this inner circle c2 and the denominator z minus a whole to the power minus n plus 1 dz. Z minus a equals to r being the circle c1. Okay, this will be actually c2. b1 is equals to 1 by twice pi I c2 fz dz. So if you take the first term, if you take n equals to 1, what you get? You get b1 by z minus a whole to the power n whole to the power 1. So this b1 which is equals to 1 by 2 pi I integration over c2 fz dz, this coefficient bn is called the residue of f of z at the pole z is equals to a. This is a very important thing. The coefficient of 1 by z is b1. It is denoted by the symbol residue at z equals to b1. So note it down quickly. This one we will be utilizing many times. b1 is known as the residue. You just remember this one. Other things if you don't remember, that is also okay. These things are not used generally. You remember this expression of f of z and the value of b1 means by putting n equals to 1 you get this b1 1 by 2 pi I integration fz dz. Now if it is done, is it done? Look, methods of finding residues. So we find residues at the poles. So there may be different cases. Let's say the first case being residue at simple pole. So you know the meaning, when the power of Z will be 1, that is the simple pole. So there are two methods of calculating the residue at a simple pole. The first one being residue of the function f at z is equals to a. So the formula is limit z tends to a, z minus a f of z. This is the first method. We will be doing a lot of problems today based on this residue calculations, so don't worry. If you have been given a function in this form f of z, which can be expressed as, let's say, phi of z upon psi of z, so in the form of this ratio, where psi of a, let's say 0, but phi of a is not equals to 0, then at that situation the residue of f of z at z is equals to a will be equals to phi of a divided by the derivative of the denominator psi prime and at that point a. Okay. So this rule helps many times. The second method, generally we use the first method, but second method is also very helpful. If your denominator at that particular pole is 0, but the numerator is not 0, at that situation residue at that point will be phi of a by psi prime of a. So this is the first case. Now if the pole if the poles are having order higher than 1, not a simple pole, so let's say we calculate for a general order, let's say n, residue at a pole of order n. This is also used very much. So all of this formula you have to remember. Will solve many problems anyway, and the formula will get automatically, you will remember. You don't need to take stress for this. So it has also two techniques. Both the techniques are very useful. The first techniques, you use the formula. Let's say if you have a pole of order n, then the residue of that function at z is equals to, let's say, a is equals to 1 by n minus 1 factorial. Whatever be the order, you will do this n minus 1 factorial in the denominator. Then you will take derivative, n minus 1 is derivative. So if you have a pole of order 3, then there will be double derivative. If you have a pole of order 2, then it will be single derivative, right? Derivative with respect to z, n minus 1th derivative of the function z minus a whole to the power n f of z evaluated. You can also take limit here, but at the end also you can do evaluated at z is equals to a. You can remove this sign anyway. Second method, let's say you have a pole of order n at z is equals to a. So what you can do, you can first put, let's say, z plus a equals to t, and you can expand. Depending on the situation, you can expand it into series. Then you know this formula that b1 gives you the residue, right? So b1 means here z minus a whole to the power 1, है ना? So if you find residue at z is equals to a, that will be nothing but the coefficient of 1 upon t. Either you put z minus a equals to t or z equals to t. So if you consider this z minus a equals to something, let's say t, so it is like equivalent to writing d1 into 1 by t. So whenever you see 1 by t, the coefficient will be the residue. We'll be solving problem based on this, don't worry. For the time being, you write. There is a third case, residue when you calculate it at infinity. Residue at z is equals to infinity. This is not so much used, but for the sake of completeness, let's know the formula. Residue of f of z at z is equals to infinity. So this has the formula limit z tends to infinity minus z times f of z. This is not widely used, okay, and it has another form, the residue of f of z at z is equals to infinity. It is written in this way, minus 1 upon twice pi I integration over c f z t z. Now once you learn to find out the residues, we need to know a very special theorem which is known as Cauchy's residue theorem, and using that theorem most of your integration will get solved. So Cauchy's residue theorem is nothing but 2 pi I times sum of these residues. So you will be given some contour and you have to find out which poles are lying inside that contour. Let's say if you get 3 poles and out of those 3 poles only 2 poles are lying inside the contour, so you have to consider only those 2 poles and you have to find residues at those poles. Once you find the residues at those 2 poles, you will use Cauchy's residue theorem, 2 pi I into sum of residues, and you will get the integral. So this is how it works. Let's explore this more. You can give the heading Cauchy's residue theorem. let's say we have a simple closed curve. So I am taking a general closed curve. It may be a circle, it may be a rectangle or anything. Most of the time it becomes a circle, it remains a circle. Let's say we have this closed curve C, it is traversed in the anti-clockwise direction, and it had some poles, finite number of poles. Let's say at Z1, Z2, Z3. So you can write if, let's say, f of z is single valued and analytic in a simple closed curve, simple closed curve C, as you have denoted here. So it is finite except at a finite number of singular points. So as I have denoted, these are the three singular points, let's say. So there may be more than three also. So except at a finite number of singular points within C. If this condition holds, then we can write that integration of that function, closed integration. So we are taking the integration over a closed curve, so that is why closed integration over the curve C, fz dz will be 2 pi I times the sum of residues at poles within C. So if you have a pole, let's say outside the closed curve, then that pole will not be considered. That pole will not be considered. Only this pole will be considered. So if there is no poles within this curve, what will be the integration then? Let's say if you have any contour, within that contour the function is fully analytic, no singular point is there inside the curve. What will be the value of this integration then? It will be 0. Yes. So this is what we call Cauchy's residue theorem. So the steps are very simple. Whenever you will be given a complex integral, what you have to do? You have to first find out the poles. What is the best way to find out poles? You will set the denominator equals to 0, fine, and the particular value of z for which the denominator is 0, that those points are the poles. Now once you get the poles, you will calculate the residues at those poles by using this formula, whatever formula I have given you. And once you find the residues, you can simply use this formula 2 pi I into sum of residues. Okay. Now you see, we have taken this contour in the anti-clockwise direction. Okay, we have taken this contour in the anti-clockwise direction. If the contour is taken in the clockwise direction, then instead of this plus 2 pi I, there will be minus 2 pi I. So this formula holds when the contour is traversed in the anti-clockwise direction. Look, in general this is given, but sometimes the examiner may want to have some fun and can give you clockwise direction contour. At that time, what you have to do, you just need to add a minus sign, nothing else. All the things will remain same. this is applicable when the contour is traversed in the clockwise direction. Clear? Now there is a strong relation between the residue at infinity at some other poles. What I want to say, okay, this is an important point. Let's say we have a complex function f of z. For a complex function f of z, the residue at z is equals to infinity it is related to the residues at all other finite points, at all other finite singularities. Finite singularities means it may be z equals to 1, z equals to 2, z equals to 3, and residue at z equals to infinity is another thing. So if you know the residues at all other finite singularities other than z is equals to infinity, then we can calculate the residue at z is equals to infinity from this knowledge of this. Okay, na? So this formula is very important. Residue of f at z is equals to infinity is equals to minus sum of residue at z is not equals to infinity, residue of z is equals to zi. What does it mean? The total sum is 0. Residue of f at z equals to infinity plus residue of f at z equals to other points, the total sum is 0. So if you are asked to calculate the residue at z equals to infinity, what you gonna do? You will calculate the residue at some other finite singularities and you will just add a minus sign, that will give you the residue at z equals to infinity. So here this zi are all the singularities of f of z, all the finite singularities of f of z. Is it clear? So main thing I would like to tell you that the most important thing is this b1, coefficient of 1 by z. It is denotes the residue. It denotes the residue. B1 is the residue. So when you will do a problem by expanding the function, in the expansion the coefficient of 1 by z will be the residue. Other than that, if you go for this approach, you can do that, no issue. Then Cauchy's residue theorem and all these things. Let me give you a problem. Is it done? Tamiz, Murli, Hari, Ajay. Okay, give it a try. What is the residue at z equals to 0 of this function z cos of 1 by z? Can you tell me? Do it quickly and tell me what is the residue at z equals to 0 of the complex function z cos 1 by z. What you have to do here? What is the answer? Are you able to get it? Minus 1, coefficient of 1 by z you are getting minus 1. Let's check. What about others? F of z, z cos 1 by z. Ajay, Harry, Tamiz, Murli, what are you getting, guys? Z. Cos we can expand. 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial and so on. So this is equals to z minus 1 upon 2z plus 1 by 24 z cube minus and so on. So we know that the residue at z equals to 0 will be the coefficient of 1 by z. Residue of f of z at z equals to 0, it is the coefficient of 1 by z. What is the coefficient? It is minus half, na? I hope it is understood. Let's go to the next problem. Find the residue of f of z is equals to, let's say, z cube by z square minus 1 at z is equals to infinity. How will you do that? 0. Let's see. Look, f of z is equals to z cube by z square minus 1. So what you can do, we can expand this, right? So if you take z square common, what we have, 1 minus 1 by z square, right? So you have z times 1 minus 1 by z square to the power minus 1. So z times 1 plus x square plus and so on. So z plus 1 by z plus 1 by z cube and so on. So we can say that residue at infinity equals to minus of coefficient of 1 by z. Can you say? Because residue is equals to coefficient of 1 by z. So residue at infinity will be minus of coefficient of 1 by z. So it should be minus of 1 because the coefficient of 1 by z is 1. Understood? Yes. Let's solve this problem. The pole of the function f of z is equals to quad z at z equals to 0. Is it a removable pole, essential singularity, simple pole, f second order pole? What did I tell you how to find out poles? Whatever function you have to set the denominator equals to 0. From that you can get the position of the poles. B, essential singularity. It is not cos, it is cot. Cot we have. So cot you can represent by as cos by sine. So if you set sine z equals to 0, are you getting an essential singularity? Do it carefully. Not an essential singularity. Look at this problem. What did I tell you? We have to set the denominator equals to 0. A, removable pole. Removable or simple? Removable singularity comes when we have up to n. Once we start getting Bn, that becomes non-essential singularity or pole. So there is nothing like removable pole. f of z is equals to cot z cos z by sin z. So what is the condition of singularity? Look, if the numerator becomes 0, that is not a problem, but if the denominator is 0, that is a problem. So this is equals to sin n pi, z is equals to n pi, and this n can take values 0, plus minus 1, plus minus 2, plus minus 3, and so on. Any value it can take. So if you take n equals to 0, this corresponds z is equals to 0. Okay. So what is the formula for simple pole? If you have limit z tends to 0, z minus 0, f of z equals to limit z tends to 0, z times cos z by sin z. So this is limit z tends to 0, cos z divided by sin z by z. So limit z tends to 0, sin z by z is 1, and if you put cos z is equals to 0, so cos 0 is 1, so this value is 1. So you are getting a finite value when you calculate the residue at the simple pole. So z is equals to 0 is a simple pole. Is it clear or not? I think yes, you can also use the second method, right? Here you have this form, cos of z is equals to a is not equals to 0, but sin at z is equals to 0 equals to 0. So the formula is phi of a, so cos at z is equals to 0 divided by phi psi prime, so sin derivative is also cos at z equals to 0. So then also you get 1, and now using the second method, this one. This one. आगे बढ़ते हैं. Do this problem, very good problem. The value of the integral over c, z to the power z to the power 10 dz, where c is the unit circle with the origin as the center is. Unit circle. Look, if the direction is not mentioned, you can in general take anti-clockwise. It is not mentioned in the question, you will always take anti-clockwise direction. So this is your curve C. Tell me the answer. Deep, you are getting A. Why A? What is the reason? Tell me the reason. Ajay, what do you think? Hari, Thamiz, what do you think? Here f of z is equals to z to the power 10. So, it is in the numerator. So, it is analytic everywhere. Analytic everywhere in the complex plane. It is analytic everywhere in the complex argand plane. So, therefore, as per Cauchy's residue theorem, the integration is 2 pi I, and there is sum of residue, there is no residue, there is no pole, so it is 0. Option A. Let's quickly move on to the next question. This came in December 2012. The value of this integral, where C is a closed contour defined by the equation, traverse in the anti-clockwise direction. Here it has mentioned anti-clockwise direction. So, plus symbol will be used. Do it quickly. Y, X. So, you see, this is the contour. C is given by this 2z given contour 2 mod z minus 5 equals to 0, means mod z is equals to 5 by 2, so 2.5. So, it is a circle with center at z is equals to 0 and radius 2.5. Okay. You do it by yourself. I am just trying to draw the given contour. It is traversed in the anti-clockwise direction. So, this is your contour C. It has a radius 2.5. So, it is more than 2. So, let us say this is 1, this is 2, 2.5, 3. Option A. Okay. So, what we have done, f of z is equals to z cube by z square minus 5z plus 6. So, singularity, condition for singularity you have applied. A, everyone is getting A. Z square minus 5z plus 6 equals to 0, and from this it is z minus 3, z minus 2 is equals to 0. So, z is equals to 2 and 3. So, one pole you are getting here, another pole you are getting at z equals to 3. So, z equals to 2 is lying inside the contour. So, z equals to 2 will be taken into consideration for calculating residues. So, this is residue, it's a simple pole, right? F at z is equals to 2. Here you are also getting. Okay, let's just do this. So limit z tends to 2 z minus 2 z cube by z minus 2 z minus 3, so 2 cube by 2 minus 3 minus 8. Therefore the integral I is equals to, from Cauchy's residue theorem, 2 pi I into sum of residue minus 16 pi I. Okay, so everybody did it correctly. बहुत बढ़िया. Let's move on to the next question. Okay, do this one. The value of the integral over c sin z by z to the power 6 dz, where c is the circle with center at z equals to 0 and radius 1 unit. Not drawing the contour this time, so basic contour, we have done it multiple times. So you have to find out the value of this integral for a contour having radius 1 unit. So for this problem, which method will be beneficial? Expansion method or setting the denominator equals to 0? Which method will be useful? Expansion? Yes. With expansion the things will be easy. Otherwise, if you go for, let's say, that setting denominator equals to 0, then we have to do fifth order derivative, na? So pole of order 6. Look, whenever you see an opportunity for expansion, you will do the expansion. That will give you the result very quickly. C, very good. So f of z is equals to sin z by z to the power 6. 1 upon z to the power 6, sin z is z minus z cube by 3 factorial plus z to the power 5 by 5 factorial, and so on. So this is 1 upon z to the power 5 minus 1 upon z cube times 3 factorial plus 1 upon z times 5 factorial minus up to infinity. So what is the residue? The residue at the pole z equals to 0 is the coefficient of 1 by z. So that is equals to 1 by 5 factorial, है ना? 1 by 5 into 4 into 3, 60. 5 into 4 into 3 into 2, 120, ना? Therefore, sin z by z to the power 6 dz as per the Cauchy's residue theorem, 2 pi I into sum of residue pi I by 60. Yes, चलो आगे बढ़ते हैं. Do this problem. The value of the integral is z square by e to the power z plus 1 dz, where c is the circle, z mod z equals to 4. So lot of problems came. We are doing mostly the previous year questions, right? And you will see many problems came from complex analysis. I think maximum question came from these things. So this is one type we are doing today. Another type we will do on the next day. We will evaluate definite integrals. So to do that, this is a like initial step. So you need to understand it very carefully. C is the circle, mod z equals to 4. Mod z equals to 4. 1, 2, 3, 4. Do it guys quickly. I am just playing around. You do your work. A you are getting. Deep, Ajay, what are you getting? Murli? Z square by e to the power z plus 1. So what will be the condition for singularity? E to the power z plus 1 equals to 0. So e to the power z is equals to minus 1. This is equals to. So for what value e to the power z is minus 1? So if you take e to the power, let's say pi I, then it is minus 1. E to the power 3 pi I, then also it is minus 1. 5 pi I also minus 1. E to the power minus pi I, e to the power plus pi I, for both e to the power that value is minus 1, right? Either you consider I pi or minus I pi. So it is for the odd values of pi I, so 2n plus 1 pi I for both positive and negative. Can you write it in this way? So the value of z for which the denominator is 0 is given by plus minus 2n plus 1 pi I. So if we put n is equals to okay, 0, 1, 2, 3 and so on. So if you consider the value of z, if you put n equals to 0, you get plus minus pi I. If you put n equals to 1, you get plus minus 3 pi I. If you get n equals to 2, plus minus 5 pi I, 3, 7 pi I, and so on. Right. So out of these poles, can you tell me which poles are lying inside the contour? Remember this once again. We have to consider only those poles which is lying inside the contour. Here the contour is a circle centered at the origin having radius z is equals to 4. So as far as these poles are concerned, which of these poles are lying inside the contour? Look, when you go along x, we go it like 1, 2, 3, 4. When you go along y, we go like I, 2i, 3i, 4i, minus I, minus 2i, minus 3i, minus 4i. So only the first two will remain inside the contour. Only z is equals to plus minus pi I lie within the contour, and it is a simple fold, and they are simple poles. Look, pi, what is the value of pi? 22 by 7. 22 by 7 means 3 point something, so obviously less than 4. But if you consider 3 pi I, so 3 into 3 point something, so 9 point something, so obviously it is coming out of the contour. So 3 point something means we can say more than 3. So around here one pole is here, so let us say this is z is equals to plus pi I, and here let us say another pole z is equals to minus pi I. So 3 pi I will lie somewhere far away from the contour. So we need to consider those poles only which are lying inside the contour while calculating residue. So let us calculate the residue for z is equals to plus I. So for z is equals to plus I, what will be the residue? So residue at z is equals to pi I, we can use this simple formula. So limit z tends to pi I, phi of z by psi prime of z. है ना? So phi of z is z square and psi prime is e to the power z plus 1, the derivative is e to the power z itself. So z square by e to the power z at z is equals to pi I. So pi I square is minus pi square divided by e to the power I pi. E to the power I pi is minus 1. So this is pi square. Now if you calculate the residue for z is equals to minus pi I, so residue at z is equals to minus pi I, limit z tends to minus pi I, phi of z, psi prime of z. I am doing the same mistake again and again. So this will be your z square by e to the power z at z is equals to minus pi I. So what will you get? So here now we will be getting minus pi square by minus 1. So it will become plus now. Sorry, minus c. So it is again plus pi square. Therefore, using Cauchy's residue theorem, I is equals to 2 pi I times sum of residue at poles within C. 2 pi I pi square plus pi square. So 2 pi square 2 into 2 4 pi cube I. Option C. How D it is C na? Pi square and pi cube. So this was a very good problem, right? चलो आगे बढ़ते हैं. Let's move on to the next question. Do this one. The value of the contour integral. Look here, already 1 by 2 pi I multiplied. Yeah. So when you will calculate 2 pi I into sum of residue, so it is like this factor will take care of. Do it. So unit circle traverse in the anti-clockwise direction. The rule is simple. Set the denominator equals to 0. Find out the poles. Separate out the poles which are lying inside the contour. Calculate the residue at those poles only. Then apply 2 pi I into sum of residues. This is in brief what you have to do. e to the power z is equals to cos z plus sin z equals to minus 1. E to the power z is equals to not cos z plus I sin, e to the power I z equals to na. E to the power z is simple real function na. E to the power I z is equals to cos z plus I sin z, but e to the power z is not same, yeah. Here it is e to the power z. C you are getting minus 8 by root 3. Yes, C is the correct option. Let's see how we can do it. So for the time being, let's consider this integral part is the f of z. Just ignore 1 by 2 pi I for the time being. F of z is equals to e to the power 4z minus 1 divided by cos hyperbolic z minus 2 sin hyperbolic z. So let's evaluate this. E to the power 4z minus 1 divided by cos hyperbolic z is e to the power z plus e to the power minus z by 2 minus 2 is multiplied, so e to the power z minus e to the power minus z divided by 2 and this 2. So what you get at the end? This is equals to e to the power 4z minus 1, this 2 is coming to the numerator. Look, e to the power z minus e to the 2 e to the power minus z, so minus e to the power z, and here it is plus 2 plus 1 3 e to the power minus z minus e to the power z. So let us now apply condition for singularity. Condition for singularity will apply. So setting the denominator equals to 0, 3 to the power minus z e to the power z is equals to 0. So this gives you e to the power z is equals to 3 to the power z, so e to the power 2z equals to 3. So what we can write? E to the power 2z is equals to 3. So you can write 3 into 1. Do you imagine? It is like 3 into 1. So 3 we can write e to the power ln 3 and 1 e to the power I times twice n pi. So you may ask, what is the requirement of writing this extra 1 separately? Why we are writing extra 1? Because if you don't consider this, you get only one value, na, e to the power ln 3. Now this 1 is multiplied just to show you that we can get more than one values. Out of them, e to the power ln 3 will give you one value. Is it understood? Tell me, Mulli, Hari, Deep, the logic behind taking 3 into 1 equals to this. Why you are not only writing e to the power ln 3? Is the logic clear to you? Therefore, z is equals to half times ln 3 plus I times 2 n pi. If you only write ln 3 e to the power ln 3, then you will get only half ln 3. Actually that value is only lying inside the contour, but for the sake of generosity or general purpose, we have to write all the poles. So you will have infinite number of poles, but only half ln3 will lie inside the contour. For n equals to 0, z is equals to half ln3. Only this pole lie inside the contour, because for the other, because it is a unit circle, so for the other poles it will go beyond the contour. How to, where we have to use this logic? Everywhere you have to use this logic. If it had -3, what you would have done? 3 into -1. So if you want to write a general expression, what do you write? Look, for an example, sin theta is equals to, let's say, 1. So if you want to write, let's say, sin pi by 2, then it is 1. But if you want a general value, what do you write? We write sin 2n plus 1 pi by 2, right? This way we write. Now what do you write? Okay, negative sign is coming, but we write it in terms of n for getting a general values. So the same thing applies here. Getting the point, Harry? Let's say, fortunately for this, the contour is having one unit only. If the contour is big enough, if the contour would have been given, let's say, very big, having radius, let's say, half ln3 plus 2 pi I, then you have to consider the second pole also by putting n equals to plus 1 or minus 1. Is it clear or not? It is like the value of the function is repeated multiple times, like in the case of sin pi by 2 is 1, then I think in 5 pi by 2 is also 1, and if you just repeat it, you get 1 again and again. So those values also you need to calculate, we need to consider. So every time you will try to calculate a general term, whenever exponential or something you get, you will try to calculate a general term and only take those points which are lying inside the contour. I hope this is clear. So it is a simple pole. So residue of f at z is equals to half ln3. This is equals to, what you can use? You can simply use the formula phi of z by psi prime of z. So 2 e to the power, we are putting z is equals to half ln3. So it is in the form of phi of z by psi of z. 4z, so that will give you 2 ln3 minus 1 divided by psi prime, so minus 3 e to the power minus z. So I am doing some step jump, I hope you understand. Minus e to the power half ln3. This one gives you 2 times e to the power 2 ln 3 equals to e to the power ln 3 square. So 3 square minus 1 divided by minus 3 e to the power minus, so e to the power ln root 3 actually with a minus sign, so 1 by root 3 minus, this is pure root 3, minus root 3 minus root 3 minus 2 root 3, 2 get cancelled, 9 minus 8, so minus 8 by root 3. So 1 by 2 pi I integration over the contour fz dz is equals to 1 by 2 pi I into 2 pi I into sum of residue minus 8 by root 3, so minus 8 by root 3. Option C is matching. Let me know if anyone has any doubt, any more doubt. In the formula sheet I gave you, na, there you can find like e to the power I pi equals to minus 1, है ना, e to the power twice pi I equals to plus 1, e to the power I pi by 2 is equals to I, e to the power minus I pi by 2 minus I. है ना, can you write it these things? Yeah, you can also write e to the power 3 pi I by 2 is also minus I, na, e to the power 3 pi I by 2 is also minus I. Chalo, do this problem. I think you can do it in within a minute. For a complex variable z and the contour C, mod z equals to 1 taken in the counterclockwise direction, 1 by 2 pi I into this. Tell me, I think you can do it in few seconds now. So what is the pole here? Option A, very good. What about others? Are you getting option A? look, if your concept is clear, you don't need to do anything about it. 1 by z residue is minus 2. So 1 by 2 pi I into 2 pi into minus 2. So minus 2. Look, you can do this kind of problem orally. So here your f of z is equals to z minus 2 by z plus 3 by z square. So can you tell me what is the order of this pole and what is the pole? What is the position of the pole? Deep, what is the pole? Harry, Murli, tell me. Yes, is it a simple pole? Do you think so? Just try to remember what did I tell you. In case of non-essential singularity, so f of z, we had n z minus z0 whole to the power n 0 to infinity, then you had n equals to 1 to infinity, bn z minus z0 whole to the power minus n. So what did I tell you, that if let us say m number of terms, if bn is not equals to 0, where n is less equals to m and equals to 0 for n greater than m, then we called it a pole of order m, right? So here z equals to 0, will it not be a pole of order 2, because the maximum power in the numerator of z is 2, है ना? Try to understand. So this has a second order pole at z is equals to 0, but because here also if you put z equals to 0, that is in infinity, here also if you put z equals to 0, that is also making it infinity, right? So you have to consider the maximum power. So this is also a non-essential singularity. So residue of f of z at z is equals to 0, you can use simply coefficient of 1 upon z. Coefficient of 1 upon z is minus 2. So 1 by 2 pi I integration f of z dz 1 upon 2 pi I minus 2. Option A. Is it clear to everyone? Let's move on. So this problem we have already done, na? We have done it once, I think. What do you say? We have done this problem today only. Just confirm. Chalo, usko, let's do this problem then. The value of integral I is equals to this, where C is a circle, mod z equals to 2. Denominator different? Yeah, but it is very similar, so let's ignore that problem. You can try that at home. Do this one. I think look, for this problem you can do it in two ways. In both the ways are suitable. Tell me the answer quickly. B. Are you sure it is B? C. Yes, C will be the answer. So I think which method you have used, expansion method or the normal method? Setting denominator equals to 0. Let's try expansion method. Okay, denominator method we can easily do. Let's check how we can do via expansion. Sin z divided by 2 times z minus pi by 2. Sin z we can write cos of z minus pi by 2 divided by 2 times z minus pi by 2. Cos of z minus pi by 2. Now let's say z minus pi by 2 is equals to t. So cos t divided by 2t. Let's take z minus pi by 2 is equals to t. Differential method, yes, that will also give you the result. But you see, for lazy people, expansion method is more preferable. You see, you just expand and you take the coefficient of 1 by t. So z minus pi by t. So in the formula, although I have told you that it is z equals z plus. Okay, let's go to that slide. Yeah. So although I told you that it put z plus a equals to 2, so actually this is z minus a is equals to t, right? So depending on the scenario, we can choose t and you can find coefficient of t. So for this problem, as you can see, yes, here we took z minus pi by 2 equals to t. So z equals to pi by 2 is a pole. So 1 by 2t cos t, we can expand 1 minus t square by 2 factorial plus t to the power 4 by 4 factorial minus so on. So you get 1 upon 2t minus t times 4 plus t cube times 2 into 4 factorial minus terms which we don't care. 1 by t coefficient is half, है ना. The residue at t is equals to 0. As you can see, t equals to 0 means what? Z minus pi by 2 is equals to 0 means z equals to pi by 2. So saying t equals to 0 is equivalent to saying z is equals to pi by 2. That is why we do this. The residue at t equals to 0 is the coefficient of 1 by t, that is equals to half, है ना. And z is equals to pi by 2. It is, the value is pi is 3.14, so 1.5 or something. So somewhat like here it is your z is equals to pi by 2. Two z minus pi, then what do you get? 2z minus pi if you put, but that will not be so useful, because you see in the numerator you have z. So if you put 2z minus pi, then this sin z you cannot do anything, na. But if you put, by taking 2 common, if you put z minus pi by 2, then this gives you a good function cos t, na. So residue at t equals to 0 is the coefficient of 1 by t, that is equals to half. Therefore the residue of f at z is equals to pi by 2 is equals to half, and as a result the integration I is equals to 2 pi I into sum of residue. Option C. Clear guys? आगे बढ़े. Let's move on to the next question. Has anyone done this problem via the differential method? Did anyone try via differential method? I think that will be easier, है ना. We can do it in few steps. Here you can see your phi z is equals to sin z, psi z is equals to 2z minus pi, है ना. So here pole is equals to pi by 2. So residue at this pole, phi of z, limit z tends to pi by 2 sin pi by, okay, sin z by derivative of 2z, so 2, है ना, so 1 by 2. So it is coming like easily, more easily. So both the processes are there. You can choose as per your convenience. Most of the time we prefer to do the differential, that is very straightforward, but this expansion sometimes may be shorter solution or easier solution. So I think you are quite aware of both the techniques now. Let's go for this. Like, look at this problem. This kind of problem, the differential method will be suitable. Okay, you will not think about expansion. Whenever we see cos, sine, then expansion thing will come into our mind. Okay, take this problem as homework. Okay, this will be a little bit lengthy problem. C is the circle given by mod z equals to pi, the integral evaluated counterclockwise, then value of the integral. Here z to the power 4 plus 13 z square plus 36. This will give you four roots of z, and I think all the roots will lie inside the contour. So you will take time and try it at home. So take this as homework problem. 4 roots will be there, and all the 4 roots will lie inside the contour. So you can do middle factor of this thing. Z square plus 4 into Z square plus 9 will come. You will do it by yourself. Z square plus 4 and Z square plus 9 will come. So Z will be plus minus 2i and plus minus 3i. So 4 roots will come, and all of them will lie inside, because Z is equals to pi means 3 point something, 3.14. So it contains all the poles, 2i, 3i, all will lie inside the contour. So you have to find out the residue at these points. So you will try this at home. Okay, let's move on to the last question of this day. Last question of today. Do this one. Here pole of order 2 is considered. Sin pi z square plus cos pi z square divided by this. C is the circle with radius 3 units. Do it quickly. Here I think the second formula will be used, 1 by n minus 1 factorial dn minus 1 by dz to the power n minus 1 z minus z0 f of z. So here how many poles are there and what is their order? Tell me, Deep, Ajay, Murli, Harry, what are the poles and what is their orders? So z is equals to 1 is a pole of order 2 and z equals to 2 is a simple pole, na? Z is equals to 1 is a pole of order 2 and z equals to 2 is a simple pole of order 1. So you have to calculate, and z equals to 1 and 2 both are lying inside the contour. So you have to calculate the residues at both of these points, because in the Cauchy's residue formula we have 2 pi I into sum of residues which are lying inside the contour. Let's calculate the residue of f at z is equals to 1. 1 by n minus 1 factorial. So d2 minus 1 is 1. So d dz of z minus a whole to the power n. So z minus 1 square f of z at z is equals to 1. है ना? This is equals to, this is 1. So d dz of z minus 1 whole square is getting cancelled. So sin pi z square plus cos pi z square divided by z minus 2. Z is equals to 1. Now you will get a big derivative of u by v. So z minus 2 whole square will come, u integration, sorry, v du minus u dv, na, v du. So 2 pi z cos pi z square minus 2 pi z sin pi z square. So v du minus u dv sin pi z square plus cos pi z square, derivative of z minus 2 is 1. Option B you are getting, very good. Chalo, put the value z equals to 1. So wherever you see sin, those values will be 0. Cos values will be minus 1. Minus 1 into 2 pi to minus 2 pi minus 1. 2 pi plus 1. So the second order pole is taken care of. Now let's calculate the pole at z is equals to 2. So it's a simple pole, simple formula. Cos 4 pi is 1. Therefore, by using Cauchy's residue theorem, 2 pi I into sum of residue of f at z is equals to 2, residue of f at z is equals to 1. Two pi plus 1 plus 1. 4 pi plus 1 times I. Option B is coming now. Clear? So we are almost at the end of the session. On the next day we'll be dealing with problems of definite integral. So we'll be given integration in terms of the real functions, then we'll solve those integrations via complex analysis technique. So we are stopping here today. If you have any question you can ask, otherwise we are ending the session. So thank you guys, thank you very much for joining the session. I hope you enjoyed the session and like the video, and see you guys tomorrow at 7:30 AM once again. Till then, bye bye, take care, have a great day.